Okay, so let's see. Go on to the next. Alright, so again, velocity is what we would call a vector quantity. It describes both magnitude, which in this case is the speed of the object, and also the direction. And so generally we use a little arrow to indicate magnitude. I'm sorry, to indicate direction. The magnitude is just the numerical value and whatever units it happens to be in. For example, 5 meters per second or 15 miles per hour. So this is the, this car here would be traveling 30 kilometers per hour to the east. This one is going twice as fast but in the same direction. And this one is going the same speed as the one down here, but it's traveling in a different direction. So both of them have the same speed, that is 60 kilometers per hour, but different directions. Alright, and acceleration is the rate at which the velocity changes over time. So you can have speed changing or you can have direction changing. That's important. Alright, so and both of them can change at the same time. And also there can be negative acceleration. Negative acceleration, for example, would be when something's slowing down. That's when the negative comes into play. Alright, so here's an example of the typical thing that we think of as acceleration. A car is going from 30 miles per hour to 60 miles per hour. That's what we would consider an acceleration. Here's another acceleration. This one would be negative, of course. 60 miles per hour to 30 miles per hour. Here's another one. It's staying at the same speed, right? The same exact speed, the same magnitude, but it's changing direction. So really, anytime, this is important, it's an important concept, is that anytime there's a change in direction, there is an acceleration taking place. And that's going to become important to us, for example, when we start talking about planets moving around the sun. In fact, Isaac Newton thought about that and realized there must be an acceleration taking place, and therefore, if you go back to Newton's second law of motion, if there's an acceleration taking place, there must be a force acting on that object. And then this last possibility is changing speeds. See, we're going from 30 to 60 miles per hour, but also changing directions at the same time. All right. So uniform acceleration is when you have constant acceleration. This is the typical acceleration that we're going to encounter. Like, for example, free-falling objects. Remember, that means an object moving up or moving down. Free-falling objects all have the same constant acceleration. And yeah, so let's... this is just a little talk about the background of forces. When a long time ago, several thousand years ago, Aristotle, who was a Greek philosopher and Greek scientist, although the definition of science has definitely changed since then, he believed that heavier objects fall faster than light objects. But it turns out he was completely wrong about this. He didn't take into account the idea of air resistance. If you eliminate air resistance, all objects fall with the same constant acceleration. We'll get to that in just a minute. Also, he believed that objects that are moving horizontally, like a ball rolling across a table, a flat table, needed a constant force. And so he really didn't get this idea of inertia that Galileo realized, 1,500 years later. Okay. The problem with Aristotle, and this is a good thing to think about for a little bit, is 2,000 plus years ago, this idea of Greek science, and we should really put that in quotation marks, because for them, science relied on thinking alone and didn't rely on experimentation. Experimentation is really the beginning of modern science, and that starts with our friend Galileo. Okay, so Galileo and some others around the time of Galileo, Kepler as well. So Galileo, using this modern idea of science, that where you have to actually, not only come up with an idea, but actually prove it through experimentation. This is what we would consider the scientific revolution. This is why science has been so successful. So Galileo, making some observations from experiments that he had performed, he realized that all objects fall at the exact same rate. And he realized that no force is required for uniform horizontal motion. A ball rolling across a table will just continue to do so, and it doesn't need a force to keep going. Now, the reason the ball slows down, of course, and we now know from Isaac Newton, is that there is a force of friction acting on the ball, and that's what slows it down. But if there were no friction, the ball wouldn't even roll. It would actually just continue to move in a straight line, until it came to the end of the table. And this idea of inertia, you can apply to objects moving in space. An object moving in space, far away from any gravitational field, will just move in a straight line, basically forever. And that was Galileo's idea of inertia, which turns out to be will turn out to be Newton's first law of motion. This is really the centerpiece of modern science, is that reasoning is based upon experimentation, or measurements of physical quantities. So what a force is a push or a pull that is capable of really accelerating an object, and the overall effect is basically a vector sum. You add up all the different forces. If one force is pulling in one direction and one force is pulling in another direction, one of those directions you have to call negative. I'll do an example of this shortly. It turns out that there are, when you think about forces, this is like kind of a big picture idea, there are really just four fundamental forces in nature. Gravitation, which of course Isaac Newton knew about. About 200 years after Isaac Newton, we learned a lot about electromagnetism, electricity and magnetism acting as one force. And then there are, in the 20th century, we found that there are two more forces, one called the weak nuclear force, which we'll get to when we get to chapter 13. The weak nuclear force is responsible for radioactive decay. And then there's this thing called the strong nuclear force. This is the strongest force in nature, although it acts over a really short distance. That is the distance inside the nucleus of an atom. And this force is what binds the nucleus together. For example, it binds protons to protons. The two protons, for example, are both positively charged. They don't want to be next to each other because of the electromagnetic force. And so the strong force binds them together. And there's also something else we found in the nucleus of atoms called the neutron. And the neutron also carries this strong force, just like the proton does. Let's see. This is all about horizontal motion. When we look at well, let's just concentrate on this concept of inertia. All right, so it's a measurement of an object's tendency to resist changes in motion, which include rest. Like if an object is at rest, it's going to stay at rest. That's almost a statement of Newton's first law of motion. All right, unbalanced and balanced forces. So let's take a look at a satellite. Satellite's moving along to the right, let's say. It's going to continue to do so unless there's a force acting on it. Let's see. So whatever direction the force is, that will change the motion in the opposite direction. And now let's turn to falling objects. Okay, so this is much more, the kind of thing that Galileo learned about and studied. And so this is a nice picture, because what's taking place here is these snapshots of this ball or object, any object really, falling, are taken at the equal intervals of time, and yet you can see further down so if this time interval is equivalent to the time interval, let's say up here, what's taking place is an acceleration, right? The object is increasing velocity as time goes on. Now, for falling objects, there's actually two equations that describe the motion. The distance changes as 1/2 the acceleration times the time squared, and this is any acceleration in general, not just for free fall. For free fall, we know the value of the acceleration. The value gets its own little symbol. It's called little g, and that value is, of course, 9.8 meters per second squared. And so free fall, falling under the influence of gravity without air resistance. So that equation that I just showed you describes falling without without air resistance. Okay. And let's see. Do we have the speed equation? I'll do that in the next video, actually. All right.